11.2 Plant water relations. Water is essential for all physiological activities of the plant and plays a very important role in all living organisms. It provides the medium in which most substances are dissolved. The protoplasm of the cell is nothing but water in which different molecules are dissolved and several particles suspended. A watermelon has over 92% water. Most herbaceous plants have only about 10 to 15% of its fresh weight and dry matter. Of course, distribution of water within a plant varies. Woody parts have relatively very little water, while soft parts mostly contain water. A seed may appear dry, but it still has water, otherwise, it would not be alive and respiring. Terrestrial plants take up huge amount of water daily, but most of it is lost to the air through evaporation from the leaves. Transpiration. A mature corn plant absorbs almost 3 liters of water in a day, while a mustard plant absorbs water equal to its own weight in about 5 hours. Because of this high demand of water, it is not surprising that water is often the limiting factor for plant growth and productivity in both agricultural and natural environments. 11.2.1 Water potential. To comprehend plant water relation, an understanding of certain standard terms is necessary. Water potential psi W is a concept fundamental to understanding water movement. Solid potential psi S and pressure potential psi P are the two main components that determine water potential. Water molecule possess kinetic energy. In liquid and gaseous form, they are in random motion that is both rapid and constant. The greater the concentration of water in a system, the greater is its kinetic energy or water potential. Hence, it is obvious that pure water will have the greatest water potential. If two systems containing water are in contact, random movement of water molecule will result in net movement of water molecule from the system with higher energy to the one with lower energy. Thus, water will move from the system containing water at higher water potential to the one having low water potential. This process of movement of substances known as gradient of free energy is called diffusion. Water potential is denoted by the Greek symbol P psi or and expressed in pressure units such as Pascal. By convention, the water potential of pure water at standard temperatures, which is not under any pressure, is taken to be zero. If some solute is dissolved in pure water, the solution has fever-free water and the concentration of water decreases, reducing its water potential. Hence, all solutions have a lower water potential than pure water. The magnitude of this lowering due to dissolution of a solid is called solid potential, or psi S is always negative. The more the solid molecules, the lower more negative is the psi S for a solution at atmospheric pressure. Water potential psi W, solid potential psi S. If a pressure greater than atmospheric pressure is applied to pure water or a solution, its water potential increases. It is equivalent to pumping water from one place to another. Can you think of any system in our body where pressure is built up? Pressure can build up in a plant system. When water enter a plant called due to diffusion causing a pressure built up against the cell wall, it makes the cell turgid. This increases the pressure potential. Pressure potential is usually positive, though in plant negative potential or tension in the water column in the xylem plays a major role in water transport up a system. Pressure potential is denoted as psi p. Water potential of a cell is affected by both solute and pressure potential. The relationship between them is as follows: psi w is equal to psi s plus psi p. 11.2.2 Osmosis. The plant cell is surrounded by a cell membrane and a cell wall. The cell wall is freely permeable to water and substances in solution, hence it not a barrier to movement. In plant, the cell usually contain a large central vacuole whose content the vacuolar sap contribute to the solute potential of the cell. In plant cell, the cell membrane and the membrane of the vacuole, the tonoplast together are important determinants of movement of molecule in or out of the cell. Osmosis is the term used to refer specifically to the diffusion of water across a differentially or semi-permeable membrane. Osmosis occurs spontaneously in response to a driving force. The net direction and rate of osmosis depends on both the pressure gradient and concentration gradient. Water will move from its region of higher chemical potential or concentration to its region of lower chemical potential until equilibrium is reached. At equilibrium, the two chambers should have the same water potential. You may have made a potato osmometer and some earlier stage in school. If the tuber is placed in water, the cavity in the potato tuber containing a concentrated solution of sugar collects water due to osmosis. Study 11.3 figure, in which the two chambers A and B containing solution are separated by a semi-permeable membrane. A solution of which chamber has a lower water potential. B solution of which chamber has a lower solute potential. C in which direction will osmosis occur. D which solution has a higher solute potential. E at equilibrium which chamber will have lower water potential. F if one chamber has a psi of 2000 kPa and the other 1000 kPa, which is a chamber that has a higher psi. Let us discuss another experiment where a solution of sucrose in water taken in a funnel is separated from pure water in a beaker through a semi-permeable membrane. Figure 11.4. You can get this kind of a membrane in an egg. Remove the yolk and albumin through a small hole at one end of the egg and place the cell in dilute solution of hydrochloric acid for a few hours. The egg cell dissolved, leaving the membrane intact. Water will move into the funnel, resulting in rise in the level of the solution in the funnel. This will continue till the equilibrium is reached. In case sucrose does diffuse out through the membrane, will this equilibrium will be ever reached? External pressure can be applied from the upper part of the funnel such that no water diffuses into the funnel through the membrane. This pressure required to prevent water from diffusing is in fact the osmotic pressure, and this is the function of the solute concentration. More the solute concentration, greater will be the pressure required to prevent water from diffusing in numerically osmotic pressure is equivalent to the osmotic potential, but the sign is opposite. Osmotic pressure is the positive pressure applied, while osmotic potential is negative.